Hi, everyone. I guess we'll just get started here today. Welcome to another Common Lisp Study Group with the Atlanta Functional Programming Meetup. Again, I'm your host, Ram Vedam, with my friend Judd sitting over there in the virtual world. Today, we're going to be discussing Chapter 10 through 12. Well, we're going to try and get as much as we can from chapters 10 through 12 on the basic data types that are provided in the Common Lisp language, as well as their collections library and a little bit of their Lisp processing utilities. I'm just going to go ahead and just hit the ground running. Of course, right now there aren't any announcements on my head to think of. As usual, any questions that you guys have or any suggestions that you guys have, I'm always going to present this. I'm on the Lisp Discord server, has Bugram. I'm also on the functional programming Slack channel, has Bugram too as well. You guys can contact me in either place to, mention your requests, see what we can get in, and we'll keep adding to the schedule of talks that we're going through as we're going through the book and other additional resources in Common Lisp. So Chapter 10 was particularly interesting because for those of you who aren't familiar with Common Lisp, Common Lisp has a standard foundation that we've talked about over the last 10 chapters, functions, macros, the special operators that are available, some variables, being able to create variables for structures. We had a little bit of a talk about dynamics and special variables last time. But of course, as we all know, when we're making real programs at the end of the day, I think the book gave a best quote actually from Fred Book's: representation is the essence of programming. And that is that the foundation of any good programming is really, can you make data structures? How can you make data structures? What data structures are built into the language that you could leverage? Often, sometimes it's easier to have those data structures available for you because the language implementers can take significant time and effort to make them as efficient as possible and as reliable as possible. Of course, you can also make them from scratch yourself if you have that foundation ahead of time. Common Lisp itself is no different than most modern programming languages. In fact, it has, the most standard primitive data types along with some composite data types in their standard library. A couple of things that might be a little different, of course, people can, interrupt me and, correct me if I'm wrong. But a couple of things that are a little different with Common Lisp versus other languages is for example, with numbers. Numbers, it has all your standard, numbers, integers, complex numbers. It has rational representation. In fact, Common Lisp is the first language I've used where it actually supports fractions. That is, if you specify something like n divided by 4 here, it'll actually reduce to its most primitive, fractional form. In this case, 5/2. Or if you do, 2/4, it'll do 1/2. It actually allows you to even add fractions together. So it'll go ahead and allow you to use primitive operations. It is an actual data type inside the language, which I thought was pretty cool. I haven't seen this in other languages often. Other languages normally do like truncation when they do division, especially when it's in this kind of infix notation, but Common Lisp does not do that. It reduces it as if it's its own data type. Of course, Common Lisp has things like, characters, strings, arrays. And arrays is a particularly interesting topic that we will visit because it includes not only vectors, but native support for multidimensional arrays. And this goes back to the history of when Common Lisp was created. Well, actually, the history of Lisp in general, because in the early days, Lisp was primarily it was designed by essentially John McCarthy, whose theoretical foundation, his background is mathematics, and he designed a theory called the recursive function theory, and used Lisp to actually study mathematical functions. So a lot of the mathematical support in Common Lisp is kind of top notch and stems from that history. Um, some additional things that it does have, of course, since it is a Lisp, and Lisp does stand for Lisp processing, we do have lists in there as a native type. Hash tables are available. You have I/O streams. You have things like files. It actually has a portable way of representing files that up until recently was unavailable in a lot of modern languages. And of course, we've talked about this ad nauseum in previous discussions. We have, of course, functions. A couple of things to note, in particular with, say, floating point and complex numbers, as I mentioned before. One, floating point, and this is definitely a good point for discussion for folks who weren't familiar with the different floating point representations. Normally, when we talk about floating point, we're talking about usually a single float, which is a 32-bit number where you have a 7-bit exponent field and a 23-bit mantissa. And what that means is you have about, precision level about maybe 15, 16 bits there for precision inside single float, single precision float. Double precision float, of course, is larger than that. Common Lisp, and I forgot about this until I started reading this chapter again today, has support for 4 different types of float. Now, that being said, whether or not, this is what the standard says. The standard says there's something called a short float, which gives you about 13 bits of precision. You have your single float, which gives you about, I think it was a standard single precision float, which is like 23 bits here. And then double and long, I think were, when I was looking at it earlier in the hyperspec, is I think about 50 bits precision. Thereabouts. Some Common Lisp implementation may not give you support for short float anymore. I don't believe, I tried testing this, for example, in SBCL. Like, I tried changing it to do short float, and it did not allow me to change it. It'll actually internally go back and cast everything as a single float data type. So even though you're able to set in common your SBCL the default floating point type, which is I think it was setf default. That's not pet name. It was shoot. It's in the book. It was, I forgot now. Mm-hmm. Was there's a way of actually checking if there's a hold on, floating format again. I have to pull it up in the hyperspec again.
What are you looking for?
In there's a way to set the actual floating point format, isn't it? Like you could specify whether or not it's
no. Well, sort of. You can set what the default read format is.
right. Here we go. I mean read default format, because when you're reading it in the data, it's going to cast it to the appropriate type. So you could do something like this, set it, but if you try to do a type of on something that could be a short float, it does not actually, like 0.1. 0.1 technically could be a short float with 13 bits of precision, and it still points out to say that it's a single float.
So first thing, just I kind of do have to butt in on that. First thing is never assign to to read default float format. I realize for demonstration, sure, but in practice, never do that
Right.
because a lot of software expects that to be single float. Um, like
I completely agree with this. Just for the sake of discussion, though, to understand what it is,
sure,
to understand that the standard does provide these four different formats. Almost nobody changes it. You should almost always use single float and up if for your precision and floating point needs. Short float, I would say, for most intents and purposes, is actually deprecated. I haven't seen it used in code that I've looked at. If there is a case where it is being used, please do let me know and let's show it because I think it's something to at least discuss about because as I haven't seen it in the real world at all.
well, a lot of that it has to do with the fact that pretty much no hardware actually has uh, support for it as in register. I mean, like a lot of 32-bit and 64-bit systems have support for single float and double float as literals,
Right.
as you
And their
can store.
FPUs have it built in, so you can have the
Right,
ability for the floating point that goes actually into the hardware implementation of the floating point
right,
representation.
yeah.
So
But
because of
very
that,
few have short float size anymore. So
so the short of it is while it is available and while it is mentioned
right,
in Peter's book, almost never use it.
right.
It is
Um,
something though that's there for historical purposes.
and there is one other thing, which is that you never have to set read default float format just to get what the implementation would do for a particular float type. You can use the exponent marker for a particular type. If you want a short float, you can do 1s1.
Yes, exactly. Yes, you can do one S, but earlier when I tried that, it keeps saying that one S is unfound.
1s1. You have to have a 1 after the
Yeah.
exponent marker.
Okay, right. Okay.
1s0, I guess, would actually
It'll
be
be
the right
one.
thing.
Yeah. You're saying
1s,
yeah, one.
yeah.
Hold on one
Type
second.
of 1s0 would tell you whatever the implementation actually uses to represent short floats. That's weird.
Yeah, I think there's a I
Yeah,
don't
you
know.
need to restart your slime.
Okay, hold on. Yeah, for some reason it just
Text, yeah, delete that buffer.
yeah, I'm gonna do that and then do this.
Yeah,
Okay.
that was weird.
Yeah. All right. So we've gone through a lot of this stuff in just when you're doing the initial exploration, almost always you start with numbers, but just for completeness sake, you have your basic addition and subtraction numbers. The other thing to note about floating point that I wanted to mention before we move on, and it's the same thing with when we start talking about operations on mathematical numbers, like complex numbers. Um, uh, if you are doing something like this and you have, let's say, a floating point number in your calculation, what ends up happening is behind the scenes, it does an implicit cast. It will convert all the previous reals into a floating point into the largest number representation for that floating point. So in this case, it should almost, oops, have to specify for, I thought, oh, F0, I guess. Maybe. Yeah. It'll convert the 1, 2, and 3 into single precision floating point before actually doing the computation. Same thing with complex numbers. Like if you have, say, a complex number which is written with a hashtag C in the reader, it's a read, and you add a number, it will go ahead and convert that integer into a complex number, which is really that's equivalent to one with no imaginary part, and it will go ahead and then do the addition. This is mainly to understand that these implicit casts will happen behind the scenes, and it could have some effect when you're going through much more complex codes. So um, just be careful about that. Be aware about that. It's the same sort of thing like with C, for example. If you're doing like a integer or floating point calculations, you're mixing types. Um, so along the point uh, with integers and rationals specifically, as I mentioned, we have a rational data type. Because of that, technically, the divide operator, which most people coming from say C, C++, or even some of the new or Java or whatever, you're used to seeing say divide actually giving you just a quotient and not the remainder, and if it is, it'll truncate the operation. Um, the divide operator in Common Lisp does not do that. It'll actually convert it into the appropriate rational number. If you want to do any sort of truncation, you would have to use the truncation function, which is normally, floor, ceiling, uh, where floor is going towards negative infinity. This is all pretty much review for those who are used to, and
You actually don't need to do that. You can actually do floor -5 too, and it'll divide and then floor.
oh yes, okay.
Yeah. Floor is actually the floor division function. It's just usually dividing by 1, so it, you know.
I think I've seen this in code before, and I just followed the pattern. So I think even Peter actually references the floor with the divide xy.
Yeah,
So,
there are slight differences really in the second return value. Um, you know,
right.
because what floor returns the quotient and the remainder
Yes,
as
that's correct.
multiple values, and when you're doing a floor to 1, which is the default, the remainder will actually be the fractional part, right? But when you're doing a floor divide by 2, it'll actually be the remainder after dividing by 2.
Okay,
So
yeah, that makes
that's why
sense.
I have a 1/2 there versus a 1 in the second one.
So let me try. I mean, I guess you're saying that it'll do the same thing here. Yeah. Okay, I see. Truncate, then ceiling is sort of the same way. Then it's ceiling division, right?
Yep.
It's
Yep.
okay. So
And there's actually also truncate division, which is rounds towards 0 in all
right.
cases.
There's truncate division, and truncate division is equal to floor for positive and ceiling for negative arguments. So you have all these different options when you're doing, and then you also have round if you're actually oh, if you want to round it to the nearest integer. So if you're doing 5.4,
Yeah. Thing to
round
note about round though is it rounds toward the nearest even, um, which can be surprising for a lot of people at first. Um, the reason for that is if you always let uh, well, not in the case of 0.5s. Sorry, to be specific. In the case of 0.5s, it always rounds toward the nearest even. Even when where a lot of people traditionally expect round to round toward the nearest number. Round in CLO round for ambiguous cases chooses, or sorry, people traditionally expect it to round up. People traditionally expect round to round up in the ambiguous case of a 0.5,
right.
but in CL it always rounds toward the nearest even, and the reason for that is to avoid skew in your data. Like if you have a bunch of randomly distributed points, but they're like ones, twos, 0.5s, threes, have a bunch of integers and 0.5s, right? And but they're reasonably randomly distributed,
Right.
and you round them all. The traditional rounding method will give a slightly outward skew to your data, right? Which wouldn't be there otherwise.
So you'd have to
Uh,
normalize anyway at that
right,
point, so
right,
before you could do it. So you don't necessarily. Well, you'd have to look at the data again to determine
right.
whether or not you have to normalize.
Yeah,
That
it just helps with some gotchas there. It's just it can be unintuitive at first. Why round is doing that?
in general, folks, if you are getting used to it, it'll get these are the functions that you would use if you need to do some sort of like rounding division, don't expect the divide operator to do that for you, like in other languages. Um, which I think is kind of nice, just because it sort of forces you to explicitly document your intent, whether you're flooring it to or sealing it, or you're actually just rounding it to the nearest even based on the use case. And it's a good form of documentation rather than having to sit down and read through all the logic related to that. There are two related functions to floor and truncate for remainders, primarily the modulus operator, which is mod versus rem. And just to give you the differences, just because I had to go look this up the first time, I think mod is for floor, and then the remainder is for the truncate function. So the reason this is particularly important is if you, for our example earlier, for positive operations, these two will be identical. But if you make them into negative, because of floor going towards negative integer, rounding to the nearest negative integer, this will definitely look kind of unfamiliar to folks. And the reason because of that is because remainder is going towards the nearest negative integer, and mod is just doing the absolute value. And Michael gave a comment here. Round 0.50. Huh. Interesting. Cool.
Right, that's the rounding towards evens that I
That's
was referring
rounding
to.
towards evens. Yeah, thank you, Michael. That's
Yeah,
so in
these.
Python you have something similar to that. So
Yeah,
that's pretty cool. I just learned something. Um, let's see. Now, going back to my notes. Yeah. So you guys probably have seen me in past meetups and our chats use incf a lot when I am incrementing a counter variable. Like, let's say that I have a global dynamic variable here. There are functions. Incf is actually, and it's decaf for decrementing, are both actually in-place modification macros. So they're equivalent to actually calling the setf star x 1 plus, So the cool thing about this is and the reason I'm bringing it up is if you need to really just do an incrementation, you can almost always just do 1 plus number, and a lot of times when you're doing iteration, this will become probably more useful for you rather than using incf or decaf accordingly. So that's it about numbers, actually, for the time being. The other things about this chapter that were particularly, I think, notable for folks here is the characters. A little note about character encoding. So originally, characters encodings in Common Lisp were ASCII, but the standard itself does not actually dictate, what the representation of characters should be. Because it doesn't mandate like that, a lot of implementation in these days, because Unicode has become sort of like the standard for native character encodings, they've actually changed their character implementations to use Unicode. I think the only one that I know of right now off the top of my head is Allegro from Franz, but I think SBCL2 as well, but I wasn't sure.
yes,
So
SPCL uses Unicode for its characters.
So internally, its structure is a code point in Unicode, is what you're saying.
Well, that's difficult to know unless you start really looking inside. I'm pretty sure. Yeah, I'm pretty sure SBCL is uses, unless you're using base char strings, which is like the ASCII range. SBCL is using UTF-32 strings internally. Last I checked.
Okay, cool. So there you have it, folks. In case you need some sort of like background support for libraries, one library that I've often seen used in the wild, um, in third-party libraries I've downloaded, is something called Trivial UTF-8. This deals with the portable way of representing UTF-8 across different implementations. I do encourage those of you who really need to deal with character manipulation to check it out, just because I think it handles quite a few of the edge cases between different implementations regarding Unicode. For character comparisons, and this is something particularly useful to know, Common Lisp has two sets of character comparisons, one that is case sensitive and one that is case insensitive. And to show the differences here, obviously, I'm just going to, show you the simple example for equality. You have something that if you use character equal with the equal sign, and you try to compare lowercase a with uppercase a, you're going to get nil. That's because obviously one is uppercase and the other one's lowercase. That's your case-sensitive operator. For its counterpart for case-insensitive changes, you can just use char equal. And this has also equivalent comparisons in the string case too as well. So so you could do string equal from, and you'll see that it's nil, but if you do string equal case insensitive, you'll see that they're equal strings. The reason I bring this up is early on when I started doing Common Lisp, I always ended up implementing case insensitivity, which is like use string down case, which will make everything lowercase, and then do an equal between the two, which is EQLP between the two. But you don't have to actually do this if you know the different operators, and that's actually kind of useful. So the standard library already provides you a lot of the case insensitive situations, a lot of the case sensitive situations too. So don't try and re-implement that which is already available there for you. Finally, before we move on to collections, the things related to strings, primarily the string comparison functions that I mentioned earlier, they actually have an ability to allow you to compare specific substrings inside of the string that you're actually looking at. So the example that I've seen is let's say that you have something called Lisp is, you have two strings that you're comparing. You just want to compare the first two, the first word in the second string and the string above. So you can actually specify starting from 0 in the first string, going till end, and then say start from 0 in the second string and end in the third, is I think like 3, and it'll actually 3. I think it was 2. Interesting. And it will go through and actually grab the subsequence underneath, and it will compare the two and then return. Right now, I might be messing up my arguments here.
Hey, Ram, I think that the N2 is probably you probably want to give it the index of the first character that's not in the string.
Right. Thanks.
Sure.
Oops. Hold on. Yeah. I've just made this optional. There we go. But essentially, it's just doing substring comparison. It has a lot of those built into its interface, the string equals and the string comparison operators. So there's no need for you to like call subsequence, which we'll be talking about in chapter 11. And that's creating the actual subsequence itself. Underneath, it's already doing that for you. which brings me up to my first point and a lot of the standard library stuff that we're exploring more. You won't see every argument, but in the book, but Common Lisp's standard library functions do have quite a few keyword arguments that you may want to look up in the documentation, and they will come of use as you start using them more and more. And I know it will take some time to actually remember them when you need them, but it's the keyword arguments are available there, so you don't actually have to write extra code to do something in Common Lisp for basic primitive day-to-day things. Any questions on this? Like, these are just basic primitive function data types. All right, cool. So moving on. Chapter 11 is more about the basic collections inside Common Lisp. As I mentioned, we have arrays, multidimensional arrays. We have vectors, tuples, hash tables, associative arrays, property lists. I mean, the list goes on about what's actually available inside the Common Lisp library for basic data structures. One thing, though, that I would like to start out with before we start talking about Lisp manipulation is essentially Peter's point about vectors being available has a good and being a very useful piece of data type inside Common Lisp. Vectors are, as you guys may know from other languages, are essentially a good integer index collection. You'll be able to you get essentially a contiguous block of memory that you could then reference based on the data type that you're actually holding in that contiguous block of memory. So if you're trying to do a vector of strings, it will just do well. Let's try vector of integers. If you want to go and access the second integer, it will just behind the scenes do a pointer manipulation to actually go and access the second element, and that's all hidden from you, much like the array list class in Java or whatever. One thing though that to make arrays to start things out is there are a couple of ways of doing this. You can do normal vector, which will just create an empty vector, call this guy out to specify static lists of objects, and it will convert and create an actual vector of that type, which in this case will be if we just simply do type of this, it'll show you that it's just a simple vector of 5. To access these guys, there's a couple of ways of doing this. So let's define a parameter. Actually, let me just mention these other two things. You can also create an adjustable vector. We're only going to deal with one-dimensional vectors here for the time being, but I will point out that, like the book mentioned, it is a multi-dimensional array. If you look at some other resources like ANSI Common Lisp, which is by Paul Graham, or the Common Lisp Hyperspec, last time I checked, most Common Lisp implementations can do up to 27 dimensions inside their array implementation. That actually goes back to, again, Common Lisp's mathematical heritage from the original Lisp. At some point, especially a lot of people were doing quite a bit of numeric programming in Lisp as well as Fortran, and Lisp was trying to be designed to be as fast as Fortran while maintaining some level of readability for the mathematical functions that you're trying to implement. So the multidimensional array design came from that. It's very close to the Fortran design of multidimensional arrays with some slight differences, but I'll refer you to the hyperspec for more information on that. To create a single dimension, though, like that's adjustable for our sake here, we could just simply call make array. And make array, as you can see in my mini buffer here in Emacs, has several keywords. You can specify an element type, like integer, float, whatever. You can specify an initial element to start things. You can specify, actually, if you're doing like a static block, you can actually specify the entire initial contents as a separate argument. You could tell it if it's adjustable, and whether or not there is something called a fill pointer. That actually is primarily for moving the capacity along. So if you're overfilling, it will actually go and expand, copy everything over, and then, well, actually, I think Common Lisp doesn't copy all the elements from the vector over. It'll just copy it into that new contiguous block and use the fill pointer to tell you where you can assign to the next value when you use vector push.
So adjustable, we'll call adjust array, which sometimes you can kind of think of it as, if you're familiar with C, realloc. So what it'll do is, if it needs to copy it over into a new memory location, it will. But if it doesn't, it'll just expand it.
It depends on how the allocator allocates between neighboring regions of contiguous blocks of memory.
Right.
If there's a free block next to it, it will probably just give you that free block and just expand it. But it really depends. I messed up something here. I think I did.
Missing a J
Oh,
there.
yeah, I'm missing a J. I just realized it. Yep. All right. So, of course, you have, these standard functions to actually add new elements into your vector. So, like in this case, I'm just adding, array, and then if you go and look at your contents, you'll see that it's actually pushing things into the array based on its location in the LIFO manner. One thing, though, to access the elements is something that this book did not go through. I didn't see it in here when I went through this again, but I wanted to show you guys here online. So, to access something in an array, you could just do, you could call this function called element sequence, and then obviously specify an index. So in this case, let's say 4. Actually, let's do 5, and you see that you can return that particular element. Another way of actually doing it, because again, this is actually a simple array. You can call aref, which allows you to specify a particular index, and it'll give you access to it. And this is slightly faster, especially when you're dealing with multi-dimensional arrays. But for simple arrays, like what I was showing before, like let's say that you have a static array, or a static vector. Like let me specify this array 2. Let me do just a static vector with an initial element, initial contents. Oh, specify this has 5 instead of 10 because, sorry. All right. So let me just make sure that we get simple vector. Okay. So in this case, when you have a static simple vector of 5 elements, you can use something that's really fast, and I've for fast access, something called svref, which will take in a simple array vector and an index, and this behind the scenes will actually do pointer manipulation directly.
Yeah.
Can I?
Yeah.
Yeah, go ahead.
we both have the same complaint about this, actually.
I've read this. I actually read
Don't
this
use
from
svref.
Common Lisp. So this is straight up from the suggestion that I read in in Paul
Yeah.
in Paul Graham's book on it.
No, you're right. SVRef is good in particular cases. However, there's a problem with simple vectors, not SVRef, but simple vectors in general, which is you can't specialize the type of a simple vector, which means if you want type specialized vectors, you can't use SVRef. And type specialized vectors are important if you actually do really care about like efficiency and statically allocating exact amounts of space for things and ensuring the sanity of your API. And so you can't use SVRef and have fixed typed vectors, unfortunately. And so SVRef.
I didn't get that sense when I was reading through the hyperspec on simple vectors. Like, is there a problem with the simple vector? Like,
Yeah.
So
Yeah,
simple vectors are just vectors that are not specialized. So
Yeah.
basically they can hold any sort of data type, which actually makes aref a lot faster in most cases. Like, basically never use SVRef because at best case scenario, it's just as fast as aref. Worst case scenario, it's slower.
Yeah.
okay, so you're saying that aref should be number one for array access, and
Absolutely.
then the next one is probably ELT, and then if you really need to, is
There's no reason really
Yeah.
to do SVRef. There's absolutely no reason.
There is, in theory, a case in which SVRef would technically be.
I can think of
no.
apply, and that's it.
Right, yeah. Like, there. The thing is, there are cases in which simple vectors, right, could be faster or not faster, probably, but perhaps more efficient because they don't use any kind of type specialization. So which means their type is known to always be, it's a vector of pointers, right? Just internally, you always know that. Whereas with like aref, it does have to figure out if it's a vector of pointers or a vector of floats or a vector of whatever. And so in that particular sense, in the sense that since SVRef is simple enough to not be specialized on type and that it will always be a vector of pointers, SVRef could be faster in that particular case. But in practice, what you actually care about more is the fact that it's well-sized, and if you're declaring the type of your array to include the element type ahead of time, just about every good Common Lisp compiler has a specialized version of aref. It'll actually replace every occurrence of aref with that's specialized to vectors of that particular type, and that will be even faster than either SVRef or just regular old generic aref. So
okay, so behind the scenes, by using aref, we'll get some optimizations for free that SVRef doesn't get at all, primarily because it doesn't have any type information to actually go make an informed decision. Okay.
Exactly.
So I've used I'm presenting to you guys what I've used based on what I've read on it. The thing about what was mentioned here is it in chapter 11, a lot of the times for sequence manipulation, he almost always, even with vectors, said use ELT, which I think is wrong. I think ARF would be much faster than ELT for element along a sequence collection.
If you've typed the variable, as in you've declared it to be of array type, there's no reason why ELT would be any slower than aref. But yeah, if you haven't given a type, yes, ELT has to dispatch, determine that if it's a list or a vector, or if your implementation supports it, some other kind of sequence. And yeah, in that case, it would have to be slower. The overhead there probably isn't too high, but yeah, if you know you're dealing with arrays, use aref.
The problem that I have with some of the sequence functions, for example, like ELT, is the fact that accessing a vector is very different. Like accessing a random element in a vector is very different performance-wise from accessing an arbitrary element in a list. So whenever I see code that uses ELT, I kind of wonder, well, why don't you just use, if you know that it's an array, just use aref. And if you don't know, like either one, you're probably performing badly, because if you're like just doing random access on a list is code smell, to me. So I don't
It
even know how to
definitely is a
explain
code
this.
smell because you're incurring a linear time cost regardless, right? Based on, I
Right.
mean,
Well,
you're with
the
with
thing
the
is,
linked list.
like when I see ELT, it tells me that you want random access.
Right.
Generally, not always. Like there's definitely some cases where you want ELT, but generally ELT tells me you want random access. If you want random access, why are you not using an array?
Yeah,
That's kind of the vibe that I get from that.
I think the only reason ELT exists is to complete the generic sequence protocol.
Right.
But because we don't actually have extensible generic sequences, the generic sequence protocol, as far as just random access into a generic sequence, just doesn't make any sense since we don't have extensible sequences. And so the only type of sequence where you would want to be doing random access is an array anyway.
So so folks who aren't familiar with the sequences, because even in this chapter and a lot of the books, when you start Common Lisp development, you'll end up realizing that there's a very generic sequences library inside Common Lisp for manipulating collections, and I'm going to be showing just a few of them here. But the basis of it is it can work on both vectors as well as lists. In fact, just as a little bit of a historical note, when the standard template library was being designed, if you look at the earlier work of Alexander Stepanov for C++ and even Ada, he actually got a lot of his generic algorithms inspiration from how Common Lisp was being designed for its sequences library. And I can refer to you guys on some of that if you guys are interested in it. But the point is it follows sort of the same approach. And that is, you should not need to care necessarily about the underlying representation. If your generic function knows how to access a particular variable based on its inner representation, that being abstracted away, then you have a very efficient generic algorithm that can work on a class of types. This is the same sort of algorithmic abstraction that you will see when you do generic programming in other languages, whether it be C++, Ada, or even some of the newer languages that support the ability for you to create generic functions, like Julia even. But that being said, the reason I bring this up is again, goes back to just my own, experimentation with this. And when I saw the access difference, because we will do a couple of these test programs just to illustrate some of this. If you do, I think I even have one, like say factorial. Let's see if I have this one. No, it's something else. For now, I will continue, but I will at the end, if we have time, I will show you guys a test program that I had that essentially used ELT originally, and when I switched it to AREF, it was a night and day difference in terms of its access. But I'm going to try. I switched it to SVREF, but I'm going to try it with AREF next time just to make sure that I see the same performance difference. So moving on. So we've seen some basic collections here for vectors. You have your standard, ability to count your vectors. So let's say that you want to count the number of ones inside of a vector that we just created: 1, 1, 2, 1, 3, 5, 1. And it'll go and go through and actually iterate through the entire sequence quickly and just find all the common elements and aggregate them. So there's a couple of other functions like that. Like if you want to find the index inside of a sequence where 3 is located, and you do 5, 6, 7, 3, 5, 6, 7,
That
8.
would be position, not find.
What?
That would be position, not find, if you're looking for the index. I get them mixed up all the time. That's the only reason I know.
Thank you. Position, not find. Okay,
Yeah,
so if
find
you want
tells you if it's there.
Yeah. Right, and find tells you It'll
like
just
it
return whether
finds
or
it.
not it's there, or it'll return nil if it doesn't exist.
Yeah. The value for that is if you start adding custom, tests or keys or things like that, it returns the thing that matched,
Right.
Yeah,
which is really useful.
that was a unfortunate example in that position of 3 just happens to be also the 3.
Yeah. Yeah, the position of 3 is on the fourth.
Yeah.
It's the fourth cell. I didn't didn't do that on. I did that completely.
Yeah, that's great.
Just to show folks that I did. This will actually, let's say that we made this. It'll tell you position 3 is a fifth element. So you could see that again. Common Lisp, like C, does 0 indexing. It does not do 1 indexing. We're not Pascal here. We don't do that. Hit first index is always 0, not 1. And the other thing is of course we have the ability to remove items from sequences, and it will return the sequence with all the items removed, and it will return the type that you specified in them, and you got substitute too as well. So if you wanted to go and substitute, you specify the new value, the old value that you want to replace, and the sequence, and then you'll return the actual sequence with the new value. These are all pretty basic, but there are generic functions. Like I could switch this guy from a vector to a list, and it will work. And that's because internally, vector and list are both essentially subclass from sequence, but as Elijah mentioned earlier, the Common Lisp library does not have this concept where you could do user-defined sequences that are extensible. So we'll come more to that later on when we start doing some more practical examples, because that is an important note to make of. So you know what some of its limitations are.
Just a quick note on the whole sequences bit.
Go ahead.
Not to draw it out too much, but the standard is vague. So basically it says a sequence is either a list or a vector or another implementation defined thing. So, and you'll see the standard do that a lot. It'll say,
yeah, if I remember correctly, the specific wording is something like list and vector are both subtypes of type sequence, but they're not an exhaustive partition.
Right.
Right.
Which basically says that, for example, SBCL does offer the concept of extensible sequences, and a couple of other implementations do as well. But you'll see that often in the standard, where some things coming from other languages can seem very abstract. Just earlier today, we were having a discussion about package designators. So package designator is a thing that you find all around the spec, and you can kind of think of it as a type of, it's a string or a character or a symbol, or a package itself, or another implementation. I think it actually allows another implementation defined thing, but regardless, like you see that all around the standard, and it can be confusing coming from other languages because you don't realize that these are actually like types. When you're told a sequence that represents the sequence type, not necessarily the sequence class, but just the concept of a sequence. And the way that the standard words it allows implementations to define their own sequence, extensible sequences on top of it.
One final note on, just because I really don't want to go through a lot of these different sequence keyword arguments one at a time, because the book does a fairly good job on it. And I do encourage you guys to go through it. Again, just to show this to you guys, I'm going to just share a different screen here. How do I switch screens here? You know what? I'm just going to do this. All right. So if you, I don't know if I can do that. Oh, sweet. Okay. So in the standard sequence, all the sequence functions that I mentioned earlier, count, position, substitute, remove, all can use this set of keyword arguments. They have some sort of ability to have a test function. You have the ability to extract like the index from the sequence element. You have the ability to create, subsequences to do the interaction from, so you don't have to call subsequence directly on the collection. There's a keyword argument that allows you to do reverse iteration. So all you have to do is just say from end true, and you don't have to change your code. It'll just recognize that you're trying to do reverse iteration. And for some of the operations, like in the case of remove and substitute, you have this notion of providing a return value of the number of elements being removed or being substituted.
Well, that actually is it's limiting. It's setting a limit on the number that can be removed or substituted, is what count does. So if you only want to replace like the first 3 occurrences of something, you can count 3.
Okay, I apologize. Yes, you're right.
Yeah.
It is like, and to give a quick example of that, let me try and see if I can switch over to. I'm gonna just share my desktop. It'll be easier for this. And then let me minimize this guy. So the example that let's say that we have our substitute example, and we have 3, 2, 3, 1, and let's say that we want to replace the first one. It will only replace one of the 3s that it finds, and it won't replace the other ones. Kind of nice. Has some advantages and disadvantages, but this is definitely available to you at your disposal. So use what you need. So moving on, we have a couple of new functions that deals with predicates too as well. You can actually specify a predicate. These are higher order functions that are available for you. You could create, in general, I don't know, I've read somewhere, actually he says it right here. So this is one thing that most people, you'll see the remove if not stuff variants used in older code, but don't ever really use them. I almost always try to just use remove if instead, and then do a negation. But the remove if not is available there. That's in the standard library. You'll see it in code. You have count if not too as well. In general, you have count if, position if, remove if, substitute if. These are all equivalent to the count, position, substitute, remove functions that we saw earlier. Yeah, you have ideas like concatenation. Concatenation inside of Common Lisp allows you to specify the type. So you can actually ahead of time tell the Common Lisp to actually return a specific type of type. So if you wanted to concatenate a list and a vector and return a vector, you could do that, like the example shown here. And it will, grab the two, merge them together, and return you a single collection. You have the ability to go ahead and do that with lists on lists, any sort of manipulation. The last example actually is particularly useful. It also shows that you can, take a string and a list of characters and concatenate them too as well. And that's, I think, it can happen on some occasions, not very many, but you will see that too as well. Honestly, this chapter on collections goes through a lot of the stuff about sorting and subsequences that I really don't think there's much for me to really show, other than this is particularly important about sort. So let's say we have, I think I had, go look at my arrays. Okay, so let me set F. Let's say that we have an array, a vector of some random, numbers, and we want to sort this guy. If we do a sort array, and I did messed up here. It was sort sequence. Oh, array and some predicate.
That'd be less than, for example, is a good predicate there.
Yeah.
It's
Okay.
it's
That's
just
right.
the way you're sorting by.
Yeah, it's whether it's descending or ascending. That's right. And it'll go and return this. This thing is a destructive operation. That is, it'll do a setf behind the scenes and do an in-place sort to make it somewhat efficient. It doesn't copy any of the pointers. That's what I essentially wanted to illustrate. Stable sort, I think, does the same thing. So if we went back to what I did earlier, we set this guy up, and instead of calling sort, we do stable sort. You'll see that stable sort also has modified the array behind the scenes. It shows one thing. Technically, for all intents and purposes, while there are higher order functions in common lists, you can. This is not a functional style sort. It doesn't return a new sequence for you.
It does if you give a list, if I remember correctly.
Yeah. So code smell is if I ever see sort or stable sort without a setf, because when you do sort on a list, it might be that it has to replace that first cons and move it somewhere else. So what's going to happen there is you call sort on your list, and now it's been destructively modified, and you have more or less like unpredictable. It's not unpredictable behavior, but it's not going to do what you want.
Yeah.
So,
what really happens there is sort is defined to, I guess, probably.
Take a look at this, right? You have random list of integers here, and I just did a sort.
Yep.
On it, and
Yep.
it's still. It's still sorted, although it actually just removed the first element too.
Yep.
right, exactly. So you should, like, pretty much 100% of the time, unless you 100% know that it is an array,
Yeah.
you should always setf sort.
Yeah, like one of the things is that my understanding is that sort is defined to consume its argument, meaning you just shouldn't bother looking at whatever you passed into sort after you've passed it into sort, unless
Yeah.
it's specifically an array, in which case it still consumes its argument, quote unquote. It's defined to just modify the array in place.
Right. So that's a.
And the same thing goes for if you're using, for example, delete, or
Yeah.
pretty much any function that destructively modifies a sequence. You should always setf it. It'll always return like the new quote unquote new sequence or the modified sequence. So you should always setf.
Yeah.
Got it. So
What are
because
the algorithms behind sort and stable sort?
It's not defined by the spec. It's just required that it be, that stable sort not move things around that are considered equal, not reorder elements that are considered.
I was playing around with that. I had like a list of lists, and I was doing a stable sort with a keyword argument, and it didn't seem to be actually stable sorting it. That's why I was just wondering.
Were you I'd have to look at that, because that would be I'd need to see the code that you were using.
yeah, if you could paste that code somewhere, Michael, we could take a look at it.
Yeah, I'll try to see if I can find it. I'm also probably using on the machine I'm doing it on. It's probably a very old version of SBLC at this point. So maybe it's something that's been fixed.
It could be, but let's take a look at the code, and then we can tell you.
Right. Yeah, I'll see. If
I don't think the standard specifies what the stable sort algorithm uses, right?
It doesn't. No.
Okay, that's what I thought. I didn't think it did.
There's some people that have documented what a lot of the popular implementations use as their sort functions, but like merge sort and quick sort are pretty common. But there's no requirement in the spec now.
Okay. So let's see here. I mean, so that's it for, wrong one. Subsequences. Yes, subsequences. So as I mentioned before, you can actually take a list and like our little array list here, and then grab the list by grab a subsection of it by calling subsequence. And like, for example, if you wanted the first to the fourth elements here in the 6 element array, it'll return 256. Right, to 256 from the sorted array. This might look like slices to some of you, some of the folks from the newer languages, but it's actually, I don't think it is the same thing, like behind the scenes internally, because of the way slices actually do work. Though sliceable sequences would be a nice to have, it's not available in the Common Lisp library, at least not as far as I know. It might be in some third-party library. You can use things like copy sequences too. You have the ability to copy sequences. You have the ability to, like in this guy, foobar. You see X, it's foobar. It's the what else? Let me see. What else do I want to show off here in this example? You have the ability to like search through a collection, but search allows you to take a sequence of elements and then take another sequence, and it will go ahead and search that subsequence within the other sequence to see if it actually exists, and returns the index of the starting point where it sees the first match. And again, as with everything else, there's it has your standard interface about your test function, whether to test not, whether you're doing reverse iteration and so forth. So there isn't much to review on that. So right, okay. So Common Lisp has several mapping functions. I think we may have, I don't remember, have we touched base on any of the mapping functions here up until now? I don't think so. So I wanted to show, this is the map that's that they're showing in the book, which is the ability to like take a vector, specify, let's say that you want to multiply 2 different vectors, and it'll do essentially a component by component vector addition. Same as you'll see that it'll return, a standard vector. So let's go through this function signature. Obviously, you have the result type, which is whether or not you're making a vector or a list. You have the function, which in the case that I showed you earlier with the multiplication, that's just a standard library function. You can also specify a lambda. You can specify multiple sequences to do the kind of stage application, but it's always component by component. So like, let's say that you want to do add 1, 2, 3, 4, 5, 6, 7, 8, 9. And it will take in as many sequences as you want, and it'll go ahead and apply them in a component by component fashion. So it's almost doing columnar aggregation. So if you made this into like a matrix, it is adding them the first column, the second column, the third column. So that's how you can use that to verify some of those things. See. Obviously, with the map, you can also have reduce. You can also do reduce as well. You can specify as function. Let's say we're just doing the first 5 integers. It'll go ahead and reduce them. Map into is another type of function. This one, I've forgotten what this is. This is... Right. So map into basically aggregates all the results of a set of maps, like in the case that I showed you earlier, into a standard location. So like, let's say map into array plus, let me just do this. Map into array. What we've just done is we've just mapped into array the aggregation of the first 3 elements, and then we stored it in where it said 1, 2, 5 originally. It went ahead and replaced them with a substitution with our aggregated data. So you can actually do aggregation, stick it into a single location. It'll do some in-place substitution for you behind the scenes. That's it for collections. Any questions so far? I mean, I know we've gone through a lot here, and I think this we might be getting close to actually time. I really don't want to take too much time. So let me stop at this point, because hash tables is a new it's going to be its own can of worms, to be honest, that I want to spend some time at least discussing. Any questions, any comments, suggestions, complaints? I'm being dumb.
As far as the map function, the result type can also be nil in case you only care about side effects.
Oh yeah, that's one of those things that I don't think I ever actually saw in practice until I read some of your code. But it's useful.
Wait, could you repeat that? I didn't quite hear you.
You had mentioned that the map function could be can have a result type argument of either list or vector.
Yes.
It could also have a result type of nil in case you don't want any return value whatsoever and you only care about the side effects.
Oh, okay. So let's try this. You gave me something to try. So you said, like, okay, so in the case of map and vector, let me try this guy. Oh, right. I would have to store this into a value, right? Some sort.
Well, if you're mapping over a single vector or list, you could map print over it.
Let's see. Okay. Let's do that. Okay. That if you don't care, and you said that if you don't care about side effects, you can pass in nil, right, Michael?
Well, it's just
If you only care about side effects,
if you only care about
if
side
your
effects,
function was modifying the sequence,
Gotcha.
and you don't care about whether it has a return value or not, you could just modify the sequence and return nil.
Yes, that makes sense. That makes complete sense. Okay, so let's see. Let me try. So it's not returning a new sequence. It's just going ahead and just modifying that current sequence to return the map.
It doesn't modify anything on its own. It's literally just take this function, call it on each element in this sequence, or if you have multiple sequences, call it in parallel on each of these, and then just discard the return value.
Okay, so if you're ignoring, okay, I see. If you're not doing any sort of assignment, you can just use this guy as nil and saying, okay, just operate on this transformation and give me the result. Okay.
Well, it doesn't give you any results. It's
ignore
just
the results. Sorry, throw away the
Yeah.
results is what I mean.
Yeah.
It's just apply this function on this element and ignore whatever it returns.
Yep. Which is useful in very specific circumstances. Very useful in very specific circumstances.
Cool. That's I just learned something new today. I'm always learning something new with you guys. With Michael's code, I'm still looking at some of his stuff. So it's one thing that I will say, for those of you who are not familiar with, I'm gonna just bring this one piece up because this is a point of something I noticed. Sometimes if you guys are doing multiple predicates, and you want all or none working, there is a case to be had to at least leverage these predicate functions, which is every, some, not any, and not every, because and I've seen people just loop through their code, even in like other libraries and other languages where they could, and they have an equivalent of this. And I'm just saying for those of you, there is something around here that you don't have to loop through and apply a predicate on to do a break. Every, some, not any, and not every is very, very useful when you're trying to apply a predicate, some sort of test against an entire collection. I've used it quite a bit. I think honestly this is the cleanest way of writing writing this kind of code rather than having a for loop. But that's just me. Does anybody have an objection on that? I mean, I've just seen too many people write or going through a collection and then checking just to see if it's even and then doing a break or something like that for some reason.
Well, I mean, I'll somewhat often, probably more often than I should, use, and I guess we haven't really gotten to it. Loop has a there is and a never and an always, has there is, never, and always clauses, which do something similar if you're a bit more imperative, and they come to mind faster sometimes. But I probably could use those just about as easily in a lot of basic cases.
I think performance-wise, it should be the same.
Yeah, should be the same. Both should be the same.
It's just that this is cleaner from a maintenance standpoint. You could clearly look at it instead of saying, okay, what is he trying to do in this loop function? And if somebody accidentally sneaks in, for example, an assignment somewhere in there, and you have to go look at it and say, damn it, they did something I didn't want to do. I'm just doing a test here. It's easier to notice, at least from a code diff perspective, what's happening.
Yeah, that's fair.
So we're gonna stop here for now. Next time, I think we're gonna go through hash tables, because hash tables is definitely something we should really talk about a little bit, just because of the fact that it deals with all the different types of equality inside Common Lisp, and even then I have to have a review of the types of equality in Common Lisp, because I have to remember EQL versus equal P. EQ is pretty straightforward, just because it's just pointer comparisons.
I was going to say this earlier when you were talking about char equal.
Yes.
A good rule of thumb that I use is the longer the name of the equality operator, the more general it is. That's why you have EQ is most specific or constrained, and then you have EQL, and then you have equal, and then you have equal P, and it follows for the other ones. You saw for strings, a regular string equal with the equal sign is more restricted than the case insensitive string equal.
And by a similar metric, the more work it's doing to do the equality
exactly,
test.
which I like. I like it. The longer the name, the more you might want to specialize it more.
Right, you might want to specialize it more. Okay, that's definitely a good rule of thumb to keep a hold of. So before we go, just one quick announcement, because Michael's on. Michael, could you give just a quick, brief introduction to the Lisp Game Jam for folks at the end? here?
Oh yes, the Lisp Game Jam is a game jam that gives a generous 10 days for everyone new to game dev or not to try creating a game. It runs. I had to change the date. Last episode I mentioned it was April 13th. That actually falls on the European Lisp Symposium date, so we changed that to the following week, April 20th. And if you I will post a link in the chat as soon as I pull it up. It gives an overview of the rules and everything. Let me see here. Just a second. Okay, if you go to that link, it explains everything.
Definitely. All right. So let me just go here to show people. April
I will
20th
mention, though, that the goal is not really to create a game, but to learn how to create a game. Even if you don't think you'll finish, you'll still learn something, and it's advisable to submit something whether you're complete or not. The goal is to see how yourself improves every game jam.
Yes, and it's to sort of get into, you know, some of the common Lisp, well, any Lisp really in this case. You can use even Emacs Lisp, it looks like, to actually develop your game.
Right. This isn't specific to Common Lisp. Any Lisp will do it all.
And it again, it goes from the 20th through the 30th, 12 a.m.
Yep, that gives you 2 full extended weekends.
You guys will have fun with it. I mean, just think about some ideas. There's no theme, right?
No, in the past we tried doing a theme. We didn't get as many participants, so it's pretty flexible. Do whatever you want.
And let's let the showcase. So I'm gonna keep reminding folks, you know, as we get closer and closer. But I wanted to bring it up now, just because, you know, that way, you know, you guys can start thinking about game ideas, and we can, you know, pitch them on, and, you know, we could discuss some ways of doing things as we get closer to it. Again, I will try and do some dumb examples for basic game programming. I think Michael, you would probably be a good you know, person to at least lean in on them when we get there to discuss some of these newer ways of doing development, at least in the Common Lisp side, since you seem to be very up on top of doing Common Lisp game dev. So, but again, you know, it's 2 months away, so keep you guys just keep those ideas juicing, you know, sort of flowing inside your head, and we'll you know, sort of revisit this as we get closer and closer to the game jam. So we're now at the end. Again, thanks all for coming. Thanks all for watching. Join us next week when we're finishing up, you know, our discussion on collections and getting into some of the list processing functions that are in Common Lisp, and hopefully we'll have some even more meaningful discussion like we had today, which was fantastic. Thanks for all, you know, Elijah, Wilfredo, Michael coming in and, you know, providing some insight into some of this stuff and some of the mistakes I was making, because that's what the study group is all about. So same bad time, same bad channel, folks. Thank you so much for coming, and let's meet up again next week.
Thank you.